let's say I have a piece of rope, very long piece of rope. I tie the rope at one end along horizontally along a straight line to somewhere on far or on the right hand side, and I hold it on the left. I hold the end to the left hand side, and I shake it up and down. So if I do that, I will create what looks like a wave. I would create the string will start moving, and I'll see what looks like a wave, and I'll see a wave that actually looks like it is traveling. It is traveling to the right. So what I'd like to do is to try to understand why or how this happens. What is going on? And why do I get this wave-like motion that moves? Surely the string, the rope is still there. The rope hasn't flown away from my hand and then start flying to the right. I'm still holding on my end of the rope. So this wave that looks like it is traveling to the right, it must just be some kind of an illusion. The rope is not really moving to the right, is it? Now let me think of what happens. Now if I so first I want to try to understand why the wave appears to move to the right. So I would be holding, say, this end of the rope. So as I hold this end of the rope, maybe at this point in time I'll be pulling down. Let's say at this point in time I'm pulling down on this end of the rope. If I pull down on this end of the rope, okay, let's see what happens. So this part of the rope will come down. This part of the rope will come down. Okay. So what looks like a peak here will be pulled downwards. Okay. So this part of the rope will come downwards, but this part of the rope, which is above, which is higher up than the original level, it must have gone up when I was pulling up just now, because I kept going up and down, right? So at this point I'm pulling down, but just now I must have been pulling up. So this part of the rope would be on its way up. There would be momentum from mass here, and this part will be on its way up. So as this part comes down, the momentum in this part would move it up so that the rope will come up here. Alright, as with all the other parts there. Okay. And so these parts would have momentum that carry this bit of the rope upwards. And this part here, alright, I would have been pulled downwards just now, right, when I was moving down. So this would be on its way down. Right, so as it comes down, this part of the rope would now appear at a lower level. So we can repeat this reasoning, and we can imagine that after a short time, the rope will have each bit of the rope would have moved, and then the new appearance of the rope would look like this dashed purple curve that I'm trying to draw now. So this bit moves down, that bit would move up, and this bit would move down, that bit moves up, this bit moves down. If I now look at this new position after a short time, maybe 0.1 second, you see that if you compare this purple curve with the yellow curve, it looks like the wave has shifted a little bit to the right. Okay, and this is the reason why we have what appears to be a wave that is traveling to the right. It is because some parts of the rope move down, some other parts move up, and this keeps repeating. This kind of movement, it keeps repeating down the rope. So this and when they have this this coordinated motion, all right, they all move together in a nicely coordinated way, we get the appearance that the peak of that each peak of the wave keeps moving to the right, but actually no point on the rope, right? If you look at any particular bit of the rope, it never actually moved to the right. It is just moving up and down on the spot, right? So this if you like, you can think of this movement of the wave, or of the peak of the wave, this movement to the right, it is like an illusion, right? It is like an illusion. But what is not an illusion is that energy is indeed transmitted to the right as it moves through each bit of the rope, pulling down on the next bit, so giving kinetic energy and potential energy to the next bit of the rope, and that gets carried all the way to the right as I pull up and down. So energy is transmitted, right? But the actual material of the rope is not. Actual material of the rope doesn't travel. That's why I'm still holding on the rope, and that's why the rope is still there. The rope hasn't flown away. Okay, now that we have this understanding, let me now look at the properties of the rope, of this motion, and try to have some better understanding about things that we can measure. Now, the things that we can measure, I would be interested in. Let me write down what I would be interested in. I would be interested in things like wavelength. Right, wavelength. Now, wavelength. What is wavelength? If you look at the wave, one of the most obvious thing which we see, even if we don't think about it. I mean, one of the obvious things about wave is that there's a repeating pattern. If you look at this part, it looks the same as the next part, and that looks the same as the next part. So there's this repeating pattern, and there is a unit. There's a repeating unit. If maybe this one. There's a repeating unit here, and there's a length to this unit, and the next unit has the same length, and this unit has the same length. Now, the length of this repeating part of a wave is called a wavelength, and we usually use a Greek letter lambda. All right, in English we read this as lambda. You can think of it this as the Greek version of the English letter L. So we call this lambda. We often use this symbol lambda to represent the wavelength. Okay, so we think of it as a symbol in algebra, and we can think that it is equal to, say, 2 centimeters or some quantities. So we have just seen one quantity to describe some parts of the wave. Now, the other thing about a wave is, okay, if I think about this up and down motion, so each point on the wave or on the rope will also have an up and down motion, and the up and down motion follows the same, if you like, maybe it doesn't go up and down together with my hand, okay, but it goes up and down in the same time. All right, let's say I go up and down in half a second, so each bit of the rope would also go up and down in half a second. So there's this idea of time. Now, the time for it to go up and down once, that is called a period. The period. So this is a time for this movement to repeat itself. Okay, so we would often represent this by a capital T. Period is time for one cycle. And it is a bit like, if you recall the earlier session on simple harmonic motion, each bit of the rope goes up and down in actually what is very much like a simple harmonic motion. And in fact, for small oscillations, they're usually exactly like a simple harmonic motion, or say of a mass hanging on a spring. So that's the period, defined in the same way as in simple harmonic motion. And if you have period, we have frequency. And frequency is just a number of cycles, number of up and down every second. So that's also like with simple harmonic motion, we have a frequency there. And this is related to the period by 1 over t, because there is one cycle in the time of the period. So we have a formula there. Now, and then there is one thing very obvious about the wave, which we must not forget. If you look at the wave, as I've emphasized right from the start, the most obvious thing you see is that the wave appears to move to the right. Okay. Now, if we follow the motion, the reason why it appears to move, why we think it moves, is because our eye would, when we see a wave, our eye would focus on a pattern. Like in this case, maybe the peak of one of the peaks. And if I try to look at the peak, I will see that it looks as if it moves to the right. Okay, I see that it has this appearance that it moves to the right. That's why I think I would think that it moves to the right. And if it moves, of course, we talk about velocity. So I can think about maybe even measuring after 1 second how many meters it has moved. Okay, so we have velocity of the wave. Velocity represented by v, as always. What I like to do now is to find a formula that relates velocity to frequency to wavelength. Right? The interesting thing is that there is actually a simple formula that relates them, and this formula is given by v is equal to f lambda, and you get to see this if you learn about waves. Frequency times wavelength is the velocity. It's not obvious how this comes about, so let me try to explain. What I'm going to do is this. Okay. Let me start by looking at this point. Let's think about this point here. This point of the wave. As I have explained with the purple curve, when this point moves down, say a little bit here, another part of the rope would be moving up a bit, and further down, those parts will be moving down and then up, and then that's why the wave looks as if it's traveling to the right. So if this bit moves down, okay, and this bit moves up, it looks as if the wave has the peak of the wave has traveled a little bit to the right, and that's why we have velocity, right? That's why we get velocity. So when this bit goes down, this bit moves to the right, and then you have all the other motion that goes with it. Now, think about what happens when this point on the rope goes down all the way. As time passes, it will go down all the way to the bottom, same level as the trough. By the way, we will call this a trough, bottom, and on the top we call this a peak. The peak or the crest, right? So crest and trough, peak and trough. Right, okay, so this point here, as time goes by, it will go all the way down to the bottom, and then it will come up again. So it goes up and down, right? Simple harmonic motion. Just repeats itself, goes up and down. Now think about what happens as this goes down. As this point goes down, the apparent peak starts moving to the right. And as it continues to go down, this point continues to go down, this apparent peak continues to move to the right. Okay, this apparent peak continues to move to the right. Now as this happens, each and every point along the way is also moving up and down. Alright, but say when this bit moves down, that bit will be moving up. As this bit moves down, this bit will be moving up to give you the peak there. So as it continues to move down, the peak will move because other bits of the rope moves up. Alright, other bits of the rope moves up. And as this point comes back up, this will continue to move. Now when this point comes down and moves all the way back up to the top again, where would this peak has moved to? Where would this peak has moved to? Now that's the question I want to find out now. Could it have moved to there? Alright, let's just test out a few points. When this point moves down and come all the way back up, where would this point be in the same time? Right, when it goes down and come up, it happens during one period, right? Now, when this has moved down and come up, where would this point be? So as this moves down, we know that this point is moving up. Okay, as this point moves down, this point moves up. So after one period, this point must have moved up, come down, and back to the same point, because one period is about one cycle, it repeats itself, right? So this point would just be here again. So the apparent peak, it can't have moved to this position because this position is not at the peak. So when this has come down and moved up, where would this peak be after one period? Okay, with this understanding, I know that after one period, this point would still be here. And same reasoning, this point after one period must have come back to here. So what I need to do is, I need to find the next point that is as high as this peak. And obviously, the next point is that. After one period, that point, which is the peak here, would have come down and moved back up to the peak. So therefore, when this comes down and move up again in one period, this crest must have moved to here. So as this comes down and move up, this crest, this peak would have traveled to here. But this distance, as we have already seen, this distance from there to there is just a wavelength. That's just our wavelength. So in other words, in the time of one period, the peak has moved one wavelength. Right? The peak has moved one wavelength. So let me try and write down this in mathematics. So in the time of one period, it has moved one wavelength. So this means that the velocity must be equal to, velocity is distance over time, right? So distance is the wavelength in this case of the peak movement, and the time taken is one period. Time taken is one period. So we have this, and now if I now want to relate the period to the frequency, I know the frequency is 1 over t. So therefore, lambda over t is just okay. I'll make it out in steps. So it's just lambda times 1 over t, and 1 over t is the frequency. So therefore, this is just equal to that. So now I have our formula. Our this is an important formula, so I put a rectangular box around it that we must remember when we learn about waves.